Good afternoon, everyone. Welcome back. Thank you for joining us. We're glad that you're here. Very glad. I'm Steve.
And I'm Scott.
And
Yep, we
together
are glad you're here. We're glad you're listening and watching and subscribing and leaving comments and tell your friends.
we're Backyard Musings, Science and Technology channel.
And we're talking about a technology topic today involving lasers. So
this looks exciting, Scott. A new laser-powered wireless system uses light to deliver data at speeds exceeding 360 gigabits. Do we have your attention? It could enable faster, more efficient indoor networks while reducing interference and energy use. And so a lot of the carriers now, there'll be a satellite up in the sky and it'll come down to the station, the where the signal will come down to the station. That'll get branched out fiber optics, right, to a pedestal outside of your home. And then that comes, and so now we're talking about more fiber optics into your house. That's what these lasers are going to use. Modern life runs on fast, reliable wireless connections. Video calls, streaming, virtual reality, and connected devices all depend on networks that already support billions of users. And we talked about that this morning with the EMP blast. Most of this data travels over radio-based systems like Wi-Fi and cellular networks. These technologies have powered decades of growth, but they're running into limits. Radio spectrum is becoming crowded because of the radio signals can interfere with each other in busy indoor spaces, and energy use keeps rising as more devices come online. Would you like to know more?
We're back to the party line.
Yeah.
All right. One emerging solution is optical wireless communication, which sends data using light rather than radio waves. Light has a much larger available bandwidth than radio frequencies, does not interfere with existing wireless systems, and can be directed precisely to specific locations. These signals make it especially appealing for indoor settings such as homes, offices, hospitals, data centers, and public venues where many users need fast connections at the same time.
Lots of advantages to this, yeah. Okay, in a study published in Advanced Photonics Nexus on March 11, 2026, researchers developed a compact optical wireless transmitter designed to deliver both high speeds and improved energy efficiency. The system is built around a tiny chip containing an array of semiconductor lasers, along with an optical setup that controls how light is distributed to users. Together, these components create a scalable platform for high-capacity indoor wireless communication.
At the core of the system is a custom 5x5 array of vertical cavity surface emitting lasers, or VCSELs. These infrared lasers are commonly used in data centers and sensing technologies because they are efficient and can operate at very high speeds. They can also be manufactured in large arrays using standard semiconductor fabrication methods.
Yeah, and you probably need to modify the fab to do this. I don't know. This article doesn't go into that. Each laser in the array can be controlled independently and transmit its own stream of data. By running many lasers at once, the system dramatically increases total data capacity compared to a single light source. The entire array fits on a chip smaller than a millimeter. So we're not even talking the chip on your credit card.
Yeah.
A millimeter. I don't even know how they make this. Do they get tiny people to make this? I don't know. Making it suitable for compact wireless access points and potentially even integration into devices like smartphones.
The researchers built the chip using established semiconductor processes and mounted it onto a custom circuit board. Early testing showed that the lasers operated consistently across the array, delivering stable output and supporting high-speed modulation.
Okay. To test performance, the team created a free space optical link spanning 2 meters. Each laser had that's about 6.5 feet. Each laser had a modulation method that splits data into many closely spaced frequency channels, allowing efficient use of bandwidth while adapting to signal variations.
Out of the 25 lasers, 21 were active during testing. individual lasers reached speeds between about 13 and 19 gigabits per second. I'm assuming that's pretty fast, right?
Yeah.
Okay. When combined, the system achieved a total data rate of a little over 362 gigabits per second.
That's fast.
Yeah. Now, what is the difference between a gigabit and a gigabyte?
You've stumped the chump on that one, Scott.
Okay. All right. This is among the highest reported throughputs for a chip scale optical wireless transmitter using a free space coupled receiver. Way over my head. The researchers noted that performance was limited by the commercial photo detector used in the setup. With faster receivers, the same system could likely achieve even higher speeds. Okay.
Yeah, this is very interesting. Using multiple light beams at once introduces challenges. If beams overlap too much, they can interfere with each other and make it harder to separate data streams. To solve this, the team designed a compact optical system that carefully shapes and directs the emitted light.
A micro lens array first aligns the light from each laser. Additional lenses then distribute the beams into a structured grid of square illumination zones at the receiver. This setup ensures each beam covers a specific area with minimal overlap.
Tests showed that the light distribution achieved more than 90% uniformity across the target area at a distance of 2 meters. This structured approach allows different beams to serve different users or devices within the same room. And I want to point out, they were probably directly across. How does this affect like curves? You know, like in a fiber optical cable that might have vertical and horizontal curves to it.
Well, to quote one of my grandchildren, I have no idea. Okay, the team also demonstrated multi-user operation by activating several lasers at once. In one test using 4 beams, each connection remained stable, and the system delivered a combined data rate of about 22 gigabits per second. These results show that multiple optical links can run simultaneously without significant interference. Well, there you go.
Improving energy efficiency is critical as global data demands continues to rise. We talked about that in a segment that data centers need a lot of power, and these communities are saying no to data centers because it's taking their electrical energy, right? Traditional radio-based systems require more power to deliver high speeds, which increases cost and environmental impact.
The optical wireless system uses laser sources that are inherently energy efficient and can operate at high speeds without complex amplification. As a result, the energy required to transmit each bit of data is significantly lower than in typical Wi-Fi systems. The researchers measured an energy use of about 1.4 nanojoules, whatever that is, per bit. Roughly half of that of leading Wi-Fi technologies under similar conditions. Any idea what nanojoule is other than nano?
Yes.
Small,
A
right?
joule is a measure of energy, right?
So
and
nano
is very small, very small. It's smaller than micro.
Yeah. Okay.
The researchers emphasized that optical wireless communication is not meant to replace Wi-Fi or cellular networks. Well, the good news for Verizon, right? Instead, it could work alongside them. Optical links could be deployed in indoor spaces where high data capacity is needed, helping to reduce congestion in radio-based networks. So the fiber optics comes into your home, and then you split it with these optical links, right? Looking ahead, similar systems could be built into lighting fixtures, ceilings. Now think about this lighting fixture. What about the light pole outside as you're traveling down the street, right? Wi-Fi from the light pole. We talked about that almost 2 years ago.
Oh, you're talking about that's where you're going to get your signal from?
You could get a signal from that.
So
yes.
obviously, if you're traveling down a road, maybe not rurally, but if you're traveling in the city and there's frequent light poles, you would have a great signal, right? Is that what
it wouldn't be 5G, it would be 360G. That's how fast it would be.
Yeah.
Okay. ceilings or access points, providing fast, secure, and energy-efficient connections to many users at once. By combining compact laser arrays, high-speed data transmission, and precise optical control, this approach offers a practical path toward next-gen indoor wireless networks that deliver more performance without increasing energy consumption.
Okay.
Love it.
Sounds pretty cool.
Let's see it. I'd buy that for $1. You know what I'm saying?
Well, and you were saying about that wouldn't be good for somebody like Spectrum or Frontier or something like that, but it might make them a little bit better and maybe have them have to drop their price because
you're talking about internet. You're not talking about voice, because these lasers don't replace voice. So you'd still need the cellular towers to communicate.
Right. But just Wi-Fi in general, right?
Yeah. Wi-Fi in general would make them compete. Yeah.
Right. So, and I think that's what we need right now, because it's just, again, it's like fuel here. It's getting to be pretty pricey to have Wi-Fi in your house.
Yeah, it's true.
Anyway,
that's why I'm broadcasting from Starbucks right now. I'm on their Wi-Fi.
They have a beautiful fireplace, as you can see. So.
All right, folks, you found out my secret.
All right.
We'll see you tomorrow.
Take care, everyone. Thanks. Have a great day. We'll see you tomorrow.